Hi, 8th grade. In case you are absent on the day that we are going over Chapter 4.3 notes or, forget some of the information, I wanted to give you just a quick lecture on Chapter 4.3 so that you'd be ready for the quiz and also the final exam. So Chapter 4.3 continues on with a conversation about work and power and then simple machines, and this talks about the different types of machines and the 6 different types that we would see. There are many examples within these 6 types, but in general, you could see a lever. No, thank you, I know how to use my pen. You could see a lever, an inclined plane, a wedge, screw, pulley, or wheel and axle. Those are the 6 different types. So we're going to run through these relatively quickly because we've talked about it in class, and these notes, the filled out ones, will be online. So you can also find this information there. So a lever, you use levers all the time without really realizing it. A lever just has a bar that pivots from a fixed point called the fulcrum. This is the fixed point here. In this case, this is a first class lever. The classes of levers change based on the placement of the fulcrum, so where the fulcrum is. In a first class lever, the fulcrum is between the load, whatever you're trying to pick up, and the input force, you pushing down. So within a first class lever, you could talk about, this will analyze the mechanical advantage. Right, MA, mechanical advantage. So when the fulcrum is closer to the load, so when this moves over here, it has a mechanical advantage of greater than 1, because what that ends up doing is you have to push down for a further distance, right, which will mean that the distance over here will be shorter, but the force will be greater. So that's like levering a rock out of a hole. Remember, we talked about this when we were talking about 4.2. If I'm trying to use a lever to get a big rock, out of my backyard, I want to use the bigger lever. It will allow me to make that lever travel for a further distance. If the fulcrum is right in the middle, like it is here in this picture, it has a mechanical advantage of 1. When the fulcrum is closer to the input, if the fulcrum instead was over here, I wouldn't be able to make it move as far. The distance wouldn't be as great, meaning that the force that I'd have to put in is a little bit greater. So my input force would grow, but my output force would decrease because the distance would be greater. So it has a mechanical advantage of less than 1. That's like on a rowboat, if any of you are on the rowing team. So if I was to ask you what is the mechanical advantage of a lever, you would say it depends, right? It depends on where the fulcrum is. It could be 1, it could be plus 1, or it could be minus 1, right? It could be 1, more than 1, less than 1. So it depends on where the fulcrum is. So we've definitely used a scale before, right? One of those balance scales in science. You've probably used a lever, maybe not to get a rock out of a hole, but you might have used a lever when you're trying to take a gear off the end of a motor. Now, second class levers, you can see, sorry for messing with that, the fulcrum is on the other side of the load and the input force. So the load is now between the fulcrum and the input force. A good example of this is a wheelbarrow, right? If you have your wheelbarrow, and I'm going to switch over to my picture of a wheelbarrow, here, this is your fulcrum, where the wheel is, and you will be standing back here picking up the wheelbarrow. Right? So this will help you move large objects, big heavy objects across a yard, because rather than you having to pick it up, you can let most of the weight, most of the force rest on the fulcrum instead, and then you attach it to a wheel, right? Good invention there, and it rolls across. Remember when we were talking about how to decrease friction? This is now going back a little ways. We were able to decrease friction by having something roll or spin. So here the mechanical advantage is greater than 1. So the MA here is 1 plus, or greater than 1, because the distance increases. I'm going to pick this up pretty high from this end. The distance on over here where the load is, the load doesn't travel up very much, but I have to pick the handles of the wheelbarrow up, let's say 2 feet. The load itself only moves maybe 6 inches. So therefore, since the load is not moving a great distance, that means the force, the output force, is more than 1. In third class levers, down here, We've got the input force now. You see how these has changed here? The input force was over here, and the output force, or the load, was there. Now it's switched. The load is over here, and the input force is in the middle. They do not change the direction, and they do not increase the force. Instead, they increase the distance through which the force is exerted, meaning that you are now traveling a greater distance. You are having to bring that object, that mass, a greater distance, but apply the force the whole time. So an example would be like using a hammer or bicep curls, right? If you think of your elbow as the fulcrum, where it's pivoting from, you're holding that weight all the way extended out there. The reason that you're doing a bicep curl is to make your bicep stronger. So it actually makes sense to have the weight as far away from that fulcrum as possible, making it more difficult. So here, the mechanical advantage is less than 1. It's smaller than 1. So these do not change the direction. Because you apply the force in the same direction that the force goes. These as well do not change the direction. I pick the object up, the load, the mass moves up. However, if we go back up a little bit to first class levers, it does change the direction. I push down, the object goes up. So first class levers are the only ones that change the direction. Pulleys are really cool. We're using them in our solar cars, and pulleys will have, a grooved wheel that holds a rope or a cable. There are 3 different types. There are fixed, movable, block, and tackle. So this one has a mechanical advantage of 1, and the size of the output force is the same as the size of the input force, right? So it's exactly the same. I pull down with this much force, it goes up with this force. This does change the direction, right? I'm pulling down, it's going up. In this case, if I was standing up here on this end of the rope and I was pulling it up, it is also, the object is going up. So this does not change the direction of the force. However, in a movable pulley, however, the mechanical advantage is 2, because this can move upwards along, the pulley itself, rather, is moving upwards along with the mass. The best kind, if you're trying to decrease the force that you're having to exert, if you're trying to make it easier, would be the block and tackle. This will have a mechanical advantage of 1, 2, 3, 4. The number of pulleys determines how much mechanical advantage a block and tackle has. So if it had 8 pulleys, right, if there were 4 more, the mechanical advantage would be 8. Here, the mechanical, or the input force rather, you are pulling it downwards and it is moving upwards. Therefore, the direction does change. You'd use a pulley anytime you want to lift a heavy object straight up, right? If you're trying to get it into the back of a car or something like that, you could drive it under, let's say you had a fixed pulley and you lifted the object up and then were able to drop it into the back of a pickup truck. However, a ramp might just be a little bit simpler for that work. So one that we haven't thought about but you use all the time would be wheels and axles. Right? Those are found in doorknobs, they're found in the faucets, wrenches, the steering wheel of your car. The wheel and axle is all over the place. We use them every day. So the way these work is that you are turning this handle here. If that handle, right, is a lot bigger than the smaller radius of the axle in here. This is where the axle is. This is where the wheel or handle would be. Since this radius is much bigger than the radius of the axle, this one, the distance, is large. If your distance is large, that means the force that you are exerting is small to do the same amount of work. Here, the distance is small, which means that the force it is exerting is much greater. So you are able to do a lot less work. The way that you figure out the mechanical advantage is you divide the radius of the wheel, this thing, divided by the radius of the axle, this one. And that ratio there tells you how much more mechanical advantage using a wheel and axle, is giving you. Inclined plane, we've talked a lot about these. The one piece that we haven't talked about is calculating the mechanical advantage. The way you do it is by dividing the length by the height. So you take 3 divided by 0.6. That equals 5. You don't care about this distance here. Let's say this distance here was 2 meters. Who cares? Doesn't matter, because we are not traveling along this 2 meter distance. We are traveling 3 meters here, and we're traveling 2 meters vertically. So in order to figure out the mechanical advantage, we divide this by this. If I asked you how could you make this inclined plane even better, it would be taking this inclined plane and extending it all the way back to here, right? So that it's a much more gentle slope. So maybe this would go to 6 meters, right? And that, if this was instead 6 divided by 0.6, it would equal a mechanical advantage of 10 by doubling the length of that plane. So inclined planes we've talked about, we've used them all the time. Wedges. The way that you normally think of using a wedges is, at least for me, using a knife. If you want to cut your steak, you are not going to use a wedge that looks like that, right? That would not be a very effective wedge because it's not all that sharp. Instead, what you would do is use a wedge that looks something like that. Again, when we're figuring out mechanical advantage, we're dividing the length by the thickness. So in this one, the length and the thickness here are about the same. So the mechanical advantage would be 1. But here, it's probably something like 10 to 1, in which case this one has a much greater mechanical advantage. Really, if the work that we're trying to do is split something in half, cut something in half, we want to sharpen that knife or that axe or the chisel, whatever we're doing here, and it will do the work much more effectively because it's longer but no wider. The last two that we'll talk about, we've got screws. So really a screw is just an inclined plane, same thing as this right here, wrapped in a spiral around a cylinder. Because I'm going to try to draw this, it's probably going to turn out pretty bad. So this would be a nail, right? But then what you have is you've got those little inclined plane wrapped around the outside of that cylinder. And as you screw it in, you don't have to apply a very big force. The force that you apply is pretty small, but it's going a very long distance because it has to twist around all of this. So if we unraveled that, if we took this, and it was raveled like that, we straightened it out, it would be at least 2 to 3 times as long as the screw itself. So if we're looking at the thickness versus the length, this is much longer than it is thick, and therefore a screw has a pretty good mechanical advantage. Compound machine just combines multiple simple machines together. So here we've got a wheel and axle up here. You turn the handle, you turn that lever here, right? Actually, it's not really a lever, it's a handle. You turn it, and it's got a radius of, let's say, that big. But it's turning a small axle in here that's only that big. So comparing the radiuses, you're turning it a much further distance compared to a smaller distance here. That means the force will be greater. Here you've got one wedge here, you've normally got another wedge on the other side, and those things are pretty darn sharp. You wouldn't want to get your finger caught in there. And if you're comparing the thickness to the length, again, you'll have a decent mechanical advantage here and here. Then you've got 2 second-class levers here. You are applying force out here for this far of a distance from here to here. As you squeeze them together, the distance here is much smaller. However, when you take the mechanical efficiency of all 3 of these combined, it's relatively low. The reason why is because there's a lot of friction with all of the moving parts. So this wheel and axle probably has pretty good mechanical efficiency. This second-class lever, pretty good mechanical efficiency, and the wedge probably has pretty decent mechanical efficiency, or a mechanical advantage rather. But when you combine all 3 of these together, what you're left with is a lot of friction because we've got moving pieces here, we've got moving parts here, we've got lots of moving pieces within this. So with all that friction, it's not as efficient, there's a lot of friction to overcome, and therefore the mechanical advantage is not quite as great. Hope this helped answer some questions, and please let me know if you have any more.